Hey everyone, and welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help out our channel and it also helps us reach others in need of assistance with these topics. So what we have going on in today's video is that we're looking at structural analysis and we're going to be looking at statically determinate beam reactions. And this will be our 7th part in this series. So what we have going on is this picture on the left, and we are tasked with determining the reactions in the horizontal and vertical directions for the pins at A and C. And we are also told that B up here is a hinge. So whenever you have a hinge member, either a frame or a beam or this two-piece member here, you want to see if you can determine any of your reactions before actually breaking apart your member at the hinge, in this case forming two members. So I'm going to go ahead and I'm going to throw on my assumptions for my reactions. I'm just going to assume AY is upward, and I'm going to assume CY is upward, and I'm going to assume A sub X is to the right, and I'm also going to assume C sub X is to the right. And if you get these assumption arrows wrong, no big deal. You'll get a negative answer for your value. So can we determine any of these four reactions before breaking the member at B? Well, yes, we can. If we sum moments at A, for instance, we can get C sub Y, because C sub X goes directly through point A since they are in line with one another, and A sub X and A sub Y also drop out because they go right through point A. So whenever you can determine any of your reactions before breaking your member at the hinge, try to do that. So what I'm going to do is I'm going to sum moments about A, and since we have to be in equilibrium, everything has to be equal to 0. I'm going to take counterclockwise as positive rotation and everything clockwise is negative. So with this moment equation, we really only have one applied force of the 6 kilonewtons per meter, and then C sub Y showing up in my moment equation. So the 6 kilonewtons per meter of force will be rotating clockwise about point A, so it will be minus 6 kilonewtons per meter times the distance it runs, which is 4 meters, and then multiplied by its distance from its center to point A, which the center of a rectangle or a uniform force will just be half the distance it runs. So it'd be 4 meters divided by 2, which gives me 2 meters. And then I have C sub Y. I have assumed upward, so it will be rotating counterclockwise about point A, so that would be plus C sub Y times its distance, its perpendicular distance over to A, so that would be 3 meters then. And that's all I would have for my moment equation, equal to 0. So pretty easy equation to solve for. C sub Y is your only unknown, and it pops out to be a positive 16 kilonewtons, which means I assumed the correct direction as up. So there's one of my 4 reactions already, and I haven't even broken this thing at the hinge yet. So can I find anything else? Well, yeah, I can go ahead and I can find A sub Y, because I've already got C sub Y. Let's find A sub Y. Well, I'm going to find A sub Y by just summing forces in the vertical direction, since it is my only remaining unknown in the vertical direction. So I would have A sub Y assumed upward plus C sub Y, which is upward at 16 kilonewtons, which they have to cancel with each other to be equal to 0. So that means I have A sub Y assumed in the wrong direction. So A sub Y is in fact going downward 16 kilonewtons. So I'm just going to go ahead and exchange that for a downward arrow. So I have 2 of my reactions already solved, and then I just need to find my other 2 of A sub X and A sub X and C sub X. So I can't really solve for these as shown. I can't sum moments because they're both going to show up in a moment equation. If I sum about B, they're both going to cancel if I sum about A or C as shown up here. And I can't really sum forces in the X direction because, well, they're once again 2 unknowns. So what I'm going to do is that since I have a hinge at B, I'm going to break this into 2 portions. The first portion will be from A to B, and the second will be from B to C. Now, I only need one of these portions here because once I find one of these reactions, I can just sum forces in the X direction to get the other. So let's just go ahead and use the vertical from A to B. So when I break it at B, this is what I end up with. If I want to draw a free body diagram very quickly, it looks something like this, where I would have A sub Y going down 16 kilonewtons. A sub X is assumed to the right. I would have my uniform load of the 6 kilonewtons per meter of lateral force. And then I would have point B up here. And since point B is a hinge, you can treat it like a pin reaction, when you break it apart. So it would be a B sub y and a B sub x up here. Now remember, a hinge does not transfer moment, so it will only act as a pin support when you break it up. It only transfers horizontal and vertical forces, well, translational forces that you can break up into the horizontal and vertical. So looking at this little member here of AB, can I solve for A sub x here? Because I really don't care much about B sub x or B sub y. I'm really targeting A sub x. Can I solve for it? Yes, I can. And I can solve for it by, well, summing moments about point B. So summing moments about point B, the only unknown that's going to appear in this equation will be A sub x, because by and B sub x go directly through B. So let's go ahead and sum moments here about B. Well, the 6 kilonewtons per meter will be rotating counterclockwise about point B. It'll be rotating like that. So it'll be positive 6 kilonewtons per meter times the distance it runs, which is 4 meters, does not change. And its distance from its center up to point B is still going to be 2 meters. And then A sub y of 16 kilonewtons goes directly through B because they're in line together, so no perpendicular distance, does not count in the moment equation. And then A sub x is my only remaining unknown, or my only remaining force that has a perpendicular distance or a rotation about point B. The way I have it drawn, it will be rotating clockwise, so it will be minus A sub x times its distance to point B, which is 4 meters, and all that has to cancel to be equal to 0. So A sub x is my only unknown in this equation, so I can easily rearrange and solve for it, and I get a positive 12 kilonewtons of force, which means I assumed the correct direction to the left. Alrighty, now with A sub x known, you can do a couple possible things here, is that you could still use the break up or the broken portion here, solve for B sub x, solve for B sub y, and then apply those B sub x's and B sub y in the opposite direction to member BC and solve for C sub x. That's the long way to do it. Or what you can do is just look at the original picture, the unbroken portion. Since now I have A sub x, I have A sub y, C sub y, I can find C sub x just by summing forces in the x direction, since it's my only remaining unknown. So let's go ahead and let's do that. So using the full portion here, if I sum forces in the x direction equal to 0, since equilibrium needs to be held, we'll take to the right as positive. Well, we would have our 6 kilonewtons per meter times the distance it runs, which is 4 meters, and then minus off A sub x, since it's going to the left, of 12 kilonewtons, and then minus off C sub y, or C sub x, sorry, because it's also drawn to the left, equal to 0. Well, C sub x comes out to be a positive 12 kilonewtons of force. So that means I assumed the correct direction. Oh, let me scroll up just a little bit. I assume the correct direction of to the left. And that would be my final reaction for this particular problem. I found A sub y, C sub y, C sub x, and A sub x, acting at my pins at the location of A and C. Now, just remember, with a hinge problem, you always want to try to find as many reactions as you can without breaking the member. And then once you get stuck and you can't find any more, just break the member at the hinge and either look at one of the pieces that you broke. And usually you can solve for more reactions using that broken portion. So I hope this video was helpful. And if you want to see more problems solved this Friday, please check out the other videos on our channel. Also, if you haven't done so already, please like this video, leave a positive comment below, and subscribe to the channel because all of that does help us out greatly. Thank you for watching, and I hope you have a fantastic day.